everyone, this video is on nuclear reactions, and so let me just start by telling you the difference in what we're about to do and what we've been doing throughout the semester. So you all have learned to balance equations, right? So if you had 8 carbons on the left side of the reaction, you had to have 8 carbons on the right. Okay, so that's what you've been learning. Well, in nuclear reactions, this is different. These are shown later because they are sort of exceptions. We don't go over these or study these quite as much. But they are very important, and they're actually easier to balance once you get the hang of them. So that's a good thing. But what's different here is that the nucleus, so we mentioned this earlier, the nucleus can actually change here. So it can go through what's called a radioactive decay, and therefore it will convert to a different isotope. Okay, and so instead of, you always had carbon on the left, you had carbon on the right. Well, this is maybe different. You may have, an element on the left and a different element on the right because they have emitted one of our particles that we went over. So we looked at our alpha, beta, positron, and gamma radiation. Okay, and so what happens is we have radioactive decay is this process by which this unstable radioactive nucleus spontaneously emits radiation in the form of one of those particles. Okay, so if you take your original nucleus, it can decay and form a new nucleus plus one of our particles, the radiation that's emitted. How we balance these is that the sum of the mass numbers on the left and the right have to equal, and the sum of the atomic numbers on the left and the right have to equal as well. Okay, so let's look at an example. We're going to do an example of alpha emission and then go through all of our other particles. Okay, we know that an alpha particle looks like this, right? Okay, so if we look here, we have uranium. Has 92 protons, 238 is the mass number. So what this is showing you is that that's the sum on the left-hand side because we have no other elements. But over here, the sum has to be 238 and 92. Okay, so if we look here, we have 2 protons and we have a mass number of 4. We have 90 protons, okay, and we have a mass number of 234. So if you add up 4 plus 234, you get 238. So these are equal. Okay, if you want to put an equal sign there, that's fine. So 4 plus 234 equals 238. So that matches, okay, or is equal. 2 plus 90 is 92. So that's equal. Okay, and so that's what it's referring to when you have to balance these nuclear reactions. Okay, you could be asked these like this. So we want to write a balanced nuclear equation showing, okay, how an isotope decays to form an alpha particle. So here's our isotope, okay, and so it says it decays. So that means that it's going to break down. So we're going to start with this here. Okay, so 241, and if you go find our element on the periodic table, it's going to be 95. Okay, remember this is our protons. This is the identity of our element. Okay, this is giving you the mass number because we know it can change. Okay, this is our radioactive isotope. Okay, and that's the number of protons. It says that it decays to form an alpha particle. So you have to know what an alpha particle is. So if you need to look back at your chart, but here is the alpha particle. So if it says decay, that means you draw your arrow. Okay, it's breaking down. It's starting as one isotope, decaying, it's emitting an alpha particle. So now we want to know what has to be here. What element or new isotope are we going to be forming? Okay, well, if we go back to our rule, we have to equal, atomic number has to equal on both sides, and mass number. So if I go over here, now look, okay, I have a 2, so this has to be a 93, right? Because 93 plus 2 equals 95. Okay, and then here, okay, it has to be, oops, 237. Okay, 237 plus 4 equals 241. Okay, what's my element? Okay, this is what we know here. That is our atomic number. So it is the identity of the element. So what am I going to do? I'm going to go to the periodic table and I'm going to look for 93, and I see this. Okay, and now I know that the difference here in my nuclear reaction is I am emitting a particle. Here it's an alpha particle, and I'm going from one isotope to a different isotope in this nuclear reaction. Okay, so we already did this. 241 minus 4 is 237. 95 minus 2 is 93. And then we use the atomic number to identify the new nucleus. Okay, and atomic number is 93. Okay, and that completes the equation. All right, here is a beta emission. We know a beta particle looks like an electron, so we do the same thing here. Okay, we have a 14 and a 6 over here, and here we have a 7 and a 14. Okay, so look here, this is negative, so you have to subtract. 7 minus 1 equals 6, so that works. 14 plus 0 equals 14, right? 14 plus 0 equals 14. Okay, the big difference being here is a negative, so you have to 7 minus 1 equals 6. So this would be a balanced nuclear reaction with a beta particle. Okay, here is a positron emission. So the difference here is now it's back. This is a positive electron, if you want to think of it that way. So if I have 11 on the left, here I have 0, so this has to be 11. So 11 plus 0 equals 11. 5 plus 1 equals 6. Okay, therefore that 5 is the atomic number for boron, and so that would be our symbol there. Gamma emission is the decay of a nucleus, and it emits this gamma radiation. And if you remember from a previous video, we talked about that gamma rays have no charge and they have no mass. Therefore, if you look here, the emission causes no change in the atomic number or the mass. So if you look here, you have the same isotope on both sides because this is 0 and 0. Technetium-99 is used a lot in medical imaging, used in the hospitals and so forth, and it decays by gamma emission to form the more stable, but this is actually still radioactive, technetium-99. Okay, you can often see this where you have a gamma emission that accompanies the electron here, or beta emission. And so if this happened, it's the same thing. Everything still has to equal. So you have 60, and this is 0 and 0, so this would have to be 60. But here you have a negative 1, so you would have to have a 28 minus 1 equals 27, which equals 27. Okay, and so this 28, that's the atomic number for nickel. Okay, and so you could find that on the periodic table. Here are all of our examples that we've gone through, and like I said, we could leave some of these out, or you could put question marks and you have to fill those in. Those are kind of things you might see on your homework. Let's do one more for practice and just pretend that we're doing a doesn't look like a very good gamma there. But nonetheless, that's gamma. Okay, so if we looked at this, okay, this is another way that we could be asked the same type problem that we were just looking at. Okay, I see that I am decaying cobalt here, so if you look at 27, the atomic number of 27 goes with cobalt. And I have a beta and a gamma emission. So I know gamma is 0. Okay, and so I look at this and I see I have 0 and 0. So my mass number has to be 60 in order for me to equal 60 over here. So 60 has to equal 60. I have 0 again, so that's not going to change. But here I have a negative 1. Okay, and so I get a few mistakes here, and students will put 26 here. Okay, that would be 26 minus 1 would be 25. Okay, that doesn't equal 27. Okay, and so here it has to be 28. 28 minus 1 equals 27. Okay, and so if we find 28 on the periodic table, this would be nickel. So when this radioactive isotope cobalt decays into here's our beta particle, our gamma, and our gamma, it forms a new isotope, and this is the nickel. And whenever it decays, it wants to form a more stable isotope. All right, I hope this helps, and let me know if you have questions on these or have problems with these in the homework, because I can make more videos on those problems as well. Thank you.